Да. Welcome.
Well,
Так, хорошо.
today I will be speaking about Brauer diagrams, modular operators, and almost certainly I won't tell you anything about graphical nerve theorem for circuit algebras. So, and this talk is based on a paper by Sophie Rayner. I think this year, maybe the previous, not sure. Okay, so let me begin with the definition of Brauer diagrams. So, a Brauer diagram of the kind NM is a pair tau t, where tau is an involution on the disjoint union of two sets, one of which has n elements and the other has m elements, without fixed points. And t is just a natural number. Well, maybe 0. So, once we say the word diagram, we should draw something. So let me do it. I will draw n points on one line and m points on another. So here n equals 6, m equals, it should be like this, 4. And well, a Brauer diagram, and we connect the points which are transposed by the involution with a segment. For example, somehow like this. Yes. Well, and I can draw several circles, namely T1s. Okay. So, as we see, a Brauer diagram is the same thing as a one-dimensional compact manifold whose boundary is precisely these n plus m points. Okay. We may compose two such diagrams. For example, let me draw another diagram below and denote this diagram by D, D1. What? Tau? Tau is an involution on the set. That is a function from our 10-element set to itself that transposes the connected points.
Но еще есть параметр, отвечающий за количество окружностей.
Well, let me draw another diagram for which the upper row has exactly n points, and the bottom row has some other number of points. 2, for example. And consider some Brauer diagram. Like, for example, this one. I think this should be appropriate. And for example, with one circle. We can glue them to each other, like this. And obtain, if we denote this diagram by D2, we obtain a new Brauer diagram, D1 composed with D2. And as we see, well, this point is connected to this one, this to this one, and this to this one. And this diagram is surely of the kind 2, 4. But we obtained a new circle, so for this new composition, the number of circles T equals 4, and not just the sum of the numbers of the previous circles. This is the way we can compose Brauer diagrams.
So to compose diagram, we need n equals of both.
Yes, we need to have equal numbers here and there. Otherwise, the composition is not defined.
M equal to 6 and n equals to 2.
Well, yes. I can. Okay. So we may compose Brauer diagrams, and for sure this composition is associative because the gluing of manifolds is also associative. So we may observe that Brauer diagrams are morphisms in a category which we denote by BD, and the objects of this category are just natural numbers, also maybe 0. So we can draw just 0 points on the bottom row, for example. This should be, I think. Okay. Brauer diagrams are morphisms in a certain category. Well, what a category has is associativity and units. And unit Brauer diagrams look like this. So this is, for example, ID3. Now I want to say that Brauer diagrams are not just a category.
This is blackboard because in the previous speaker managed to crash the blackboard, and it was about a year ago.
Got it. So
He was so enthusiastic.
Okay, so Brauer diagrams form not just a category, but Brauer diagrams form a symmetric monoidal category. I think I should begin with the definition of symmetric monoidal category. Well,
two objects, 2 and 3. What is the morphism?
Empty set, no morphisms.
Okay, 2 and 4.
Well, there are many. All the Brauer diagrams are morphisms. So you got it. Thank you. Well, a symmetric monoidal category.
Пишите, пожалуйста, все-таки покрупнее чуть-чуть.
Is a category plus an operation which we denote by a will. Well, if we denote our category by C, then the will acts from C by C to C. Well, with usual properties of the product. And also, the category C should have a unit. So it's a triple of C, will, and 1. That is an object in C, for which A by 1 equals 1 by A equals A. And also the condition of symmetry. A by B equals B by A. If we forget this condition, then the category is called just a monoidal category. Well, usually when we talk about, for example, well, what are the examples of symmetric monoidal categories? Well, the simplest one is maybe the category of vector.
Простите, пожалуйста, для последнего пункта нужно, чтобы точки не были занумерованными. То есть, если мы переставляем точки, это чтобы было то же самое. А тогда их нельзя перемножать.
Yes, that is, I want to say, this category is not a strict symmetric monoidal, but lax. So there are isomorphisms, I think. They're not equal, but rather isomorphisms. I'll say it now. So maybe in the category of vector spaces with the usual tensor product. But when we talk in the course of algebra, we prove that these are isomorphisms, and these are not really not completely the same things. So usually when people talk about monoidal categories, they talk about lax monoidal categories, for which this is not just equality, but a pair of isomorphisms. And well, these isomorphisms should satisfy some naturality condition, which is a rather strange commutative diagram. You may Google it if you want. This is not really important. So, as I said, Brauer diagrams should form a monoidal category. And well, the monoidal operation, we need to define it just on objects, right? So we just concatenate. The sets, and well, as in linear algebra, you can consider tensor products of morphisms. Here you can consider tensor products of morphisms as well. And well, you will get something predictable. Okay, so Brauer diagram, the category of Brauer diagrams, is a symmetric monoidal one. So, why people actually began to study Brauer diagrams? It was begun by Brauer. And he proved a theorem, which I don't know how to prove, but it is certainly interesting. Consider a full subcategory of the category of the Brauer diagrams.
Значит, что является категорией диаграмм Браудера? Это мы фиксируем число n, и мы рассматриваем диаграмму, на которых верхние и нижние множество элементов.
Нет, мы диаграмма браузера — это морфизмы этой категории, а объекты — это натуральные числа. Вот. So, consider a full subcategory. That means that we make less objects, but the morphisms are the same. Of the category of Brauer diagrams, for which, we consider just the Brauer diagrams. For which our involution tau sends n to m. This means that these are precisely the Brauer diagrams for which no 2 points in the upper row are connected to each other. So then the morphisms from this category to to the category of vector spaces, well, with our plus and with our product, that preserve the monoidal structure. So f of a plus b equals f of a by f of b. So are just the same as the representations of the infinite orthogonal group. Of the fields K, I think. So the infinite orthogonal group is just the union of all the orthogonal groups which are embedded in each other in the usual way. So its representation are exactly the sequences of representations of ON that someone stabilize. So this is certainly an interesting fact, and that's the motivation for study of Brauer diagrams. Okay. Now I want to move on to, again, to category theorem. Of course.
Invariants because we got natural numbers, yes. I mean, I don't understand how orthogonal theorems.
Well, it's a mystery for me as well. I don't know why, but well, this is a fact. As I said, that I don't know how to prove. I wanted to mention it.
Basically, left-hand side, two categories.
This is an equivalence of categories. The category of functors from the downward Brauer diagrams to the category of vector spaces that preserve the monoidal structure.
That category you mentioned,
Uh,
what is role of this subcategory?
Oh, well, I gave a definition. It consists of the Brauer diagrams for which this is an invalue, for which one row of the points is not connected to each other. Any points of one row are not connected. This means somehow this expression means the words I'm saying.
Left-hand side, use this subcategory.
Yes, that's why I defined it. Okay, now we want to study the category of Brauer diagrams further. I want to say that it's a multi-category or a colored apparat, is they're often called multi-categories. I should begin with the basic idea. So, what a category is? It consists of objects and morphisms. Morphisms have one source and one target. Well, the morphisms satisfy associativity law, and there are unit isomorphisms. Okay. Morphisms in categories are usually just functions. So, as we know, there are not only functions of one variable which are considered in categories, but we also can consider functions of several variables. So the question is, what if we had many sources? Okay. And here's an example of this situation. consider the class of all vector spaces. We can consider several vector spaces, v1, v2, v3, for example, and take a multilinear map to another vector space. So by such a triangle that should resemble some electronics, we denote a function, multilinear function, from the product to v4. I'm just talking an example that's not too rigorous by now. So example. Well, so we can imagine such things as morphisms with many sources. We can compose them, for example, like this. F G1 G2 G3 V1 V2 V3 V4 V5. So this is what? This is F of G1 of 1 argument, G2 of 2 arguments, and G3 again from 1 argument. We can write it in another way as a composition. F composed with a tuple G1, G2, G3, and we can substitute in there 4 variables. Okay? So imagine we are talking about multilinear maps, F and G. So there certainly exists some, and we can now draw this composition in a more convenient way, maybe. F circle G1, G2, G3, V1, V2, V3, V4, and V5. Okay. I want to say that such a composition law, such compositions satisfy some condition of associativity, namely this one. Consider a larger diagram. So, such a scheme, and we denote the functions by f, g1, g2, g3, and well, h1, h2. I should draw something larger. H1, h2, h3, and here are h4, h5, and h6. So this is a function of of several variables which can be input here and output it there. So what is this? It's F circle composed with G1, which is itself composed with H1 and H2, then G2 composed with H3 and G3 composed with H4, H5, and H6. Yes? Right? We can write it in another way. It's just F of G1, G2, G3 composed with H1, H2, H3, H4, H5, H6. Is this clear that these two are the same things? So if we substitute here variables after all. So and these are clearly different things from the points of order of operations, but these are the same functions, and this is how an associativity law should look like. And well, there are clearly some units. It's just yes, and that composition law makes the class of vector spaces into an operand, right? So now, and there is an identity morphism, just vectors is sent to vector, clearly. So now I will give the definition of an operand. By now I'm defining multi-categories, which are generalizations of operands. And I've already given an example. So, definition. A multi-category is a class, for example, C class. Well, for each n, we have for each n and elements of C, maybe A1, AN that belongs to C, and also another elements. So in C, these are sources, and this is the target. Okay. Well, maybe a class or a set of morphisms. I think it's more traditional to call them maps. How do we define it? Well, map of A1, so on, AN, and A. Okay? A composition law. So this is the set of for vector spaces. This is the set of all multilinear maps from A1 from these n vector spaces to this. A composition law. Well, for example, again, for each A1, AN, A, we're going to see, and B1, 1, B2, B1, 2, B1, A1, and so on. So many Bs that give the composition. So map from Bs to the corresponding A with an index by map from again B's, but the second, A2, and so on. And also by the set of maps from A to A. So once we compose these maps, we obtain a map from all the B's to A. So this is the composition law, and this should satisfy associativity and have identities. Well, and the associativity law looks somehow like this. So this is an example, just an example. So this is an operator. Oh, this is a multi-category. Yeah. Well, what can I add to this definition? How it can be modified? At first, we can say that the order of the functions that we substitute and order of the variables that we substitute does not matter, so some kind of commutativity. In this case, a multi-category is called a symmetric multi-category or multicolored operator. I don't really want to discuss them because it makes them a little more complicated, at least for me. Although this definition is, I just said, not written, is more important for algebra. Okay. Let me give some other examples of multicolored of multi-categories. Well, I don't consider the morphisms of a category. I just consider its objects. I don't mind. That's multimorphisms. Yeah, that's I am going to say somehow a little later. Yes, it's a map from Cartesian products. Yeah, maybe I should write it down. Wait. If you want, a to the power a1 by an. Okay. So, some examples. A category is a multi-category. Well, why? I would say, so if C is a category, then the maps of A1 to A are just, well, the set of morphisms C of A1, A. And is usually denoted by home C. And the set of maps that have many sources is just empty for any A1, AN, A, and N greater than 1. So a multi-category is a category. A category is a multi-category. Okay. Now let me give a new definition Oh, no. Well, another example. This is the generalization of the multi-category of vector spaces. So let's assume that we have a monoidal category, symmetric monoidal category. Then we can make it a multi-category, which we again denote by C. And well, their maps from A1, so on, AK, and to A is just the same as the morphism from C, the morphisms that indeed connect the monoidal product. So for each monoidal category, we obtain a multi-category. On the contrary, not every multi-category can be obtained from a category. Oh, from a monoidal category. Well, I will give a rather strange example where at least it's not clear where is the category. But let me first give a definition. A multi-category with one object is an operator. How? And let me give now examples of operators. There is the trivial operator. Well, for it, so what is special about operators? How are they better than multi-categories? Well, in them, any maps are composable. So you can compose just any tuple of maps because they have the same source. Yeah, here, maybe I forgot to say that A's may be the same, for example. Just so the trivial operator, it has one object, of course. Well, maybe with object, let me denote it by A, and the set of maps whose source is A n times, and whose target is A, is just a singleton. So a set with just one element. Then all those axioms are clearly satisfied. There's just one way to define a composition law, and that's why this map is just this set of maps has a proper defined composition law. Okay, it's a trivial example and, well, a non-trivial example. It's called the small circles operator. Okay.
Small circles or small disks?
I don't think there is difference. I think this was disks rather. Yes. I don't remember how to write it, so circles. Sorry. So the small circles operate. Well, again, we have just one object. Well, let me denote it by O. So O is an operator. And the maps are rather funny. Map from A n times to A is the set of such circles, of such diagrams. A large circle and n non-intersecting small circles of varying size. So the set of all such diagrams is the unit circle, and these ones are smaller circles. Okay, how to compose such diagrams? Let me give an example. So by X denote, well, this diagram larger. That belongs to map A and A. By Y denote just this one, no, this one that belongs to map A to A. And by that denote the circle with, for example, 3 holes. So it has 3 sources and 1 target. So now we may compose them. X has 2 places, so we may substitute into it Y and Z. So how do we define it? Just in the following way. We take X, the circle that corresponds to X, and glue and paste inside it smaller versions of those 2 circles. So here it's.
I would say disks, otherwise
Yeah. So paste disks. Okay. Yeah. So this is not just a diagram. We may imagine that these are holes in a black circle. So, and paste that into the second. Yes, we should order the circle because I'm using non-symmetric operators. So this was the first one, and this was the second. And here we paste Z. So just a dilated version of that, and obtain a circle with 4 holes. So it's an element of map A, and 2A. So there are 4. This is how defined this is how the composition law defined. Just this thing. So this is a non-trivial example, and we will soon encounter that the Brauer diagrams form a very similar things to this.
А можно уточнить? Все-таки, значит, объект 1, а что является этими самыми морфизмами? Размеры их, это самое, вот когда мы меняем размеры этих кружочков, это у нас получается новые мапы или какие-то из морфизмы класса?
Я бы сказал, там, давайте с точностью до подобия. Вот, с точностью до подобия картинки просто. То есть вот с подобием переводим Z сюда, а Y сюда. Сейчас, нет, тогда плохо, сейчас скажу.
То есть я к тому, что...
Нет, просто сдвигом и гамма-тетией, вот так.
Я к тому, что этих мапов довольно много, их континуальное количество.
Да.
Размеры шариков важны.
Да, их очень много. So, yes. Well, let me say. okay, let me say that those maps are defined up to homotety and movement. So no, not a movement, but parallel translations. Huh? And then there are there's a continual number of such maps for basically for each sources and targets. So we just use homotety to paste this circle inside there. Oh.
Say just one circle with 4 holes.
Any 4 holes. Yeah, this is the circle with 4 holes, but this is not the same as these 4 holes, for example.
Когда вот эта операция, то на месте 2 кружочков требуются старые, а границы стираются, и мы остается только ориентирующихся на 2 кружочка. Положение этих кружочков тоже имеет значение, разные положения кружочков — это разные элементы этого мэпа.
Можно выбить, что один из кружочков находится внутри какого-то другого.
Нет, внешне вообще освобождается.
Да, вот.
Нужно их туда вклеить, а потом забыть. Вот это слить. Получается.
So we obtain something like this.
Это разные получается.
Определение.
I said that.
Это набор кружочков с точностью параллельного переноса и это самое растяжение. Но если мы внешний круг зафиксируем с радиус 1, тогда уже разный набор кружочков, не пересекающихся, разные точки, разные элементы.
Yes, I could define this up to, for example, homeomorphisms, but then this example would be much more boring, and maybe you would obtain the trivial operator. I'm not sure. So, okay. So these are examples. And well, as I said, there is a symmetric version where the order of the circles does not matter. Then this definition would not work. However, well, as I have said, all monoidal categories give us multi-categories. That is the case with Brauer diagrams. So we will denote this multi-category with the same letters. Okay, now I should say something about the algebras of multi-categories and operates. What is this? Well, assume that we have a multi-category M. And a monoidal category, for example, C with product 1. This monoidal category is called an algebra for M, maybe C algebra, even though it would sound awkward, if there is a map from the objects of M to objects. Okay. Let me do it in another way. So there is a corresponding multi-category, C-multi. For example, it's usually here considered vector spaces. So you may imagine that C is just vector space. So this is just a map from one multi-category to another. That preserves the compositions. So the functions and the compositions. So just like a function. It's an algebra. I should give some examples, and at least for the trivial operator. What is what?
The girl.
Of this definition?
It's a film talk.
Это самое, в этой теории категории очень много, это просто определение и вопрос языка. Когда там очень незаметно, когда в какой момент это количество переходит в качество и является своим содержанием.
Как минимум я хочу объяснить, как выглядит, что операда, определенная диаграммой Брауэра, это вот circuit diagrams.
Circuit diagram.
Вот.
Например, по-русски это будет алгебра для
Наверное. Наверное. Да.
Пока идут определения, мы сами ищем.
I want to tell that the Brauer diagrams form an operate that is very similar to the small disks operate. This is the only thing I can tell about this. So at least not being too vague. Okay. Should I say okay? And well, if M was a multi-category that corresponded to a monoidal category, then this is the same thing. It's a theorem, but it's the same thing. That's just a function, monoidal function. If M was a multi-category generated by this algebras of multi-categories. So it's just a monoidal function and the rather simple thing. Okay. Indeed, why do I define algebras? I'm not sure if I can tell you much about them. Sorry. Okay, as I said, Brauer diagrams should form a multi-category. So we should be able to compose one diagram with several ones. For example, like this. So if we have one diagram and another one, we may compose them, of course, for sure. Да, тут все. So, and this is the picture. Now there is another way to draw a Brauer diagram. Namely, for example, we may draw two circles around it. So, and it would look like this. So a circle with a hole. And here we, when we compose, we have like several circles with one hole. And one large circle with several ones. And thus we would obtain something like a circle operate. However, this is not just an operate, this is multi-category, because the gluing laws don't allow us to compose any pair of morphisms, because the boundary must be the same. Okay? So, and well, and what I wanted to say, the category of circuit algebras, I have wrote by whom they were introduced, is just the category consisting of such, the category of algebras of a multi-category, and I don't think I can say today anything more because it will take pretty too long. So should I try? That's the question.
Once again, what is this picture?
A usual Brauer diagram. A usual Brauer diagram can be regarded as some map in the disk operate, but modified its disks with curves.
Сейчас, значит, это something like X composition.
So let me draw two pictures. This is a composition. This is a version. This composition. Okay. I should give some notations. This is so this is F. This is G, and this is H. So three Brauer diagrams. And I'm making an attempt to draw the composition of F and the pair G and H. Essentially the same by the definition of a multi-category that corresponds to monoidal category as this. And so we may draw Brauer diagrams inside circles, and then this composition is exactly the same. So these are two holes. Is it understandable?
То есть у нас есть Мы берем элемент операды маленьких дисков, да, который состоит из диска, внутри которого два диска.
Ну да.
Объект. И значит, в каждый из внутренних дисков мы вклеиваем диаграмму Брайла, да?
Мгм.
В один из них G вклеиваем, в другой вклеиваем H. Диаграмма F, она соединяет внешнюю окружность большого диска, значит, с двумя окружностями. Да, Миш,
Надо просто как из полосы сделать кольцо.
цилиндр.
Кольцо.
Да, но почему-то, когда значит, в этой композиции несколько аргументов справа, то у каждого аргумента, прежде чем самую прямую сумму делать, нужно помнить все-таки, что они отдельности, для каждого свое кольцо.
Ну да, это потому что надо помнить, что f это элемент мультикатегории уже. Воспринимают не совсем как диаграмму Брауэра, как диаграмму Брауэра, у которой верхняя половина разделена на части. Вот.
Количество аргументов, да.
Разве не требуется?
Что именно?
Там вставляет.
Ну да. Well, I can say a little about why this construction was done. Well, this category of algebras of this operate has a full subcategory that is somehow described by graphs. And the category of algebras of Brauer diagrams can be embedded into the category of presheaves of this subcategory. However, I think it's a long road to define that subcategory, and I'm not, and I surely don't understand it all. Где C — это мультикатегория кружочков. Сейчас. Да. Да, это вот и говорит. That's what I meant, that I depict the algebra of the multi-category of the Brauer diagrams. Thank you.
So you want to stop here.
Yeah, I would prefer to.
Ой, все уже доклад кончился. А когда же содержание было? Все языки, это все было язык.
Да, видимо так. Ну, то есть я мог бы сказать там про graphical species, но не то чтобы это поможет мне что-то выговорить. Это было бы еще языка.
It's mentioned in the paper that these constructions are related somehow to finite type not invariants.
Yes, and
Which way?
Well, that's another paper. Can say by whom. And да, я думаю, да. Well, I don't quite understand it. I didn't read it. Just a couple of pages of the first pages, so not sure.
You don't know how it works, yeah? And
Ты утверждаешь, что вот такая конструкция как-то связана с
инвариант, может быть, не совсем голословно, заложено как нет. Что-то более общее.
Ну, я как бы... Самое первое определение очень похоже на танго, которое встречается в теории узлов.
Ну, диаграмма Брауэра.
Диаграмма Брауэра, это значит какой-то
Ну,
остаток от танго.
да, на диаграммах Брауэра там можно это там, всякие съедать куски, и это так какая там вторая. Да. Ну, там есть операция подобная. Сейчас. Тому, что происходит там.
Знаем, что сверху, что снизу.
Ну, там, да, все содержательная информация забывается, соответственно, содержательная. Странно, потому что действительно в какой момент количество приводит к качеству, понятно. Значит, не объясняли, я всегда говорил, что теория категории, ну я не могу, какая-то глупость какая-то, а потом мне объяснить, что есть две вещи. Есть всякие большие категории, которые категория всех векторных пространств, или категория всех множеств. Это вещь необозримая, бесполезная, это вопрос гравитации. Есть содержательные, это то, что малые категории, где количество объектов и количество там морфизмов, они там нумеруются какими-нибудь или параметризуются какими-нибудь конечными множественными счетами или континуальными.
Или, скажем, объект 1.
Или объект 1. И тогда из них можно изготовить какой-нибудь содержательный самый предмет исследования, но дальше этого замечания тоже не продвинется.
Ну, статья, ну, тут ничего, кроме категории теории, наоборот, нет.
Ничего нет.
Ну, значит,
Ну, там вот есть какая-то важная вот, теоретика категорная.
Какие-то лингвистические упражнения, которые,
да.
в какой момент они кончаются, начинаются серьезно.
Ну, говорю, вот там была вот важная теоретика, категорная теорема, вложение вот этой самой вот категории таких вот алгебр в предпучки над некоторой ее подкатегорией, которые определяют через графы. Ну, ее объяснять долго.
А что
я ее не могу
от бесконечности? Там где-то было в начале.
Ну, вот есть O от 1, она вкладывается в O от 2 и так далее. У них есть предел.
Это прямо ортогональная группа, да?
Да. Индуктивный.
Сложение, значит, индуктивное.
Да.
Понятно даже, какие вопросы знать.
Простите.
Спасибо.
Вам тоже спасибо.
На этой радостной ноте мы, наверное, заканчиваем этот семинар в этом семестре. Первый семестр. А второй семинар, в зависимости от настроения, может еще продолжаться.
Доску я вроде не сломал, да? С петличкой. Он здесь покрывается.
Да-да-да.